Hello everyone, and thanks for being here today. In this presentation, let's start talking about the challenges of manual credit approval process, which often struggles to predict loan defaults accurately, leading to potential financial losses. Accurate loan default predictions are crucial for banks to make informed decisions, manage risk effectively, and maintain financial stability. The solution? We want to enhance the credit approval process for home equity lines by using machine learning models. The main goal is to predict potential loan defaults and to predict the bank with valuable insights for better decision making. I have explored three machine learning models: logistic regression, decision trees, and random forest. Now, let's jump into the problem definition. Loan default is a significant concern, occurring when borrowers struggle to make timely payments on their loans. This isn't just a financial challenge, it's a scenario that can lead to huge risks for lenders because they might face difficulties to recover the loan amount. Also, loan defaults can impact the borrower's credit record. This means that it becomes harder for them to secure future loans. It's a complex issue with implications for both the lender and the borrower. Now that we understand the challenge, let's talk about solutions. Our aim is to automate the assessments of whether a loan applicant is likely to default or not. To achieve this, we can leverage classification models. These models anticipate the likelihood of loan default for new applicants by learning from historical outcomes of similar cases, considering the credit and personal characteristics. Now, here's a crucial point to consider. Banks deal with several customer variables, but only a handful significantly impact the outcomes of loan default predictions. By using machine learning techniques, we expect to uncover the key variables that affect the probability of loan defaults. The home equity dataset has 5,960 recent home equity loans, with 12 variables per applicant and a binary target named BAD, indicating 1 for default and 0 for repayment. Now, let's discuss our solution approach. First, we observe that the dataset has significant percentages of missing values and outliers in pretty much all the variables. It's critical to address these data issues before model development because this can impact the model performance. For example, debt-to-income ratio has 21.25% of missing values, and the derivative report has 11.87% of missing values as well. Similarly, the liquid credit lines have 20.15% of outliers, and the derivative reports have 20.16% of outliers. Now, not all the outliers need to be addressed, because these values can be possible in some cases. For example, loan amounts above $40,000, although considered outliers, makes totally sense. However, in the case of credit line age, credit line number, and debt-to-income ratio, the outliers might not be realistic in some cases. For example, having applicants with 71 credit lines, 97 years of credit history, and a debt-to-income ratio of 203, that's definitely not realistic. To handle outliers, we apply a practical solution which is capping and clipping values to the lower and upper whiskers values of the box plot. For the missing values, we have imputation using median for numerical variables and mode for categorical variables. To understand the impact of missing values in the model performance, we added new columns for each variable with missing values. So we have true if there was an original missing value and false if not. Moving forward, let's delve into our model building approach. In the data preparation phase, I focus on splitting data for 70% train and 30% test. Additionally, it's required to scale the dataset because independent variables in this dataset have different scales. So there is a chance that the higher weights will be given to the features that have higher magnitude, leading to bias toward these features. Therefore, we fix this issue by using standard scale method, which centers and scales the dataset using z-score. When it comes to model evaluation, our criterion prioritize recall to minimize false negatives. In other words, we are focusing on minimizing the errors when the applicants will not default when the applicant actually defaults, because this type of error can lead to significant financial losses for lenders, as they might be unable to recover the loan amount. In comparison, for example, to false positives, where the impact in losing a potential customer might be less harmful. Now, let's talk about the individual models. For logistic regression, our initial model assessment yielded a recall of 70%, which improved to 80% after tuning using precision curve, with a threshold of about 0.38. For decision tree, our initial model assessment yielded a recall of 76%, and after hyperparameter tuning using research, we got a recall of 81%. Finally, for random forest model, the initial model assessment resulted in a recall of 81%, and after tuning using research, we got the highest recall of 83%. Now, as we saw before, based on recall evaluation in the three models, the recommendation for predicting loan default is definitely random forest classifier, where we got the highest recall value of 83%. However, it's essential to note that random forest models are often considered black box, meaning that the decision-making process can be challenging to interpret. To address this, we can employ feature importance techniques. These techniques allow us to gain insights into the factors influencing the model's decision. By understanding the importance of its features, we can enhance our comprehension of the model predictions and improve transparency in the decision-making process. Now, as we explore the potential benefits of implementing random forest, it is clear why this model stands out. Firstly, when it comes to accuracy, studies have consistently shown that the random forest outperforms other common models like logistic regression and decision trees in predicting loan defaults. Secondly, random forest brings increased efficiency to the table. Its ability to handle large datasets efficiently through parallel processing, making it well suited for analysis loan application and scaling up prediction tasks. Lastly, random forest is more robust in dealing with outliers and noise. This means that the risk of fraud is reduced. Now, let's delve into the key findings and insights from our analysis. The consistent feature important across all models shows that the crucial role of debt-to-income ratio has the most influential factor in impacting loan defaults. Interestingly, debt-to-income ratio also happens to be the feature with the highest number of missing values. This becomes particularly significant as the percentage of missing values highlighted in the feature importance clearly impacts the results when predicting loan defaults. Moving beyond, we identified two other variables that significantly impact loan default predictions. And these factors are delinquent credit lines and age of the oldest credit line. Notably, these variables influence substantially to the loan default probability. This aligns with the logic that older credit lines may indicate better financial stability, a point reinforced by the negative coefficient identified in our logistic regression analysis. Last but not least, let's explore the proposed business solution based on our findings. First, we recommend investing in data completeness and quality enhancement. This involves implementing data quality checks with a specific focus on critical variables such as debt-to-income ratio. Next, we suggest feature enrichment by including additional relevant features. Variables such as credit score, income, employment history can provide a more comprehensive picture of our model, improving its predictive capabilities. Moving on to the algorithm integration and model deployment, my recommendation is to integrate random forest classifier into the existing credit approval infrastructure, with a deployment able to run real-time credit assessments. In regard to continuous model monitoring and calibration, this is essential for maintaining accuracy over time. We propose implementing a continuous monitoring system to track model performance. Lastly, we recommend investigating the integration of external economic factors into the model. This includes, for example, considering variables such as interest rates, inflation rates, and economic indicators.